Okay, let's continue with the reading of structure and interpretation of computer programs. So we arrived, we finished the first chapter, and so we can start with the second one, which is titled Building Abstractions with Data. Chapter 2 starts with this quote by Hermann Weil. I think this is the right pronunciation for the German mathematician. We now come to the decisive step of mathematical abstraction. We forget about what the symbols stand for. The mathematician need not to be idle. There are many operations which he may carry out with these symbols, without ever having to look at the things they stand for. We concentrated in Chapter 1 on computational processes and on the role of procedures in program design. We saw how to use primitive data, numbers, and primitive operations, arithmetic operations, how to combine procedures to form compound procedures through composition, conditionals, and the use of parameters, and how to abstract procedures by using define. We saw that a procedure can be regarded as a pattern for the local evolution of a process, and we classified, reasoned about, and performed simple algorithmic analysis of some common patterns for processes as embodied in procedures. We also saw that higher order procedures enhance the power of our language by enabling us to manipulate and thereby to reason in terms of general methods of computation. This is much of the essence of programming. In this chapter, we are going to look at more complex data. All the procedures in Chapter 1 operate on simple numerical data, and simple data are not sufficient for many of the problems we wish to address using computation. Programs are typically designed to model complex phenomena, and more often than not, one must construct computational objects that have several parts in order to model real-world phenomena that have several aspects. Thus, whereas our focus in Chapter 1 was on building abstractions by combining procedures to form compound procedures, we turn in this chapter to another key aspect of any programming language. The means it provides for building abstractions by combining data objects to form compound data. Why do we want compound data in a programming language? For the same reasons that we want compound procedures, to elevate the conceptual level at which we can design our programs, to increase the modularity of our designs, and to enhance the expressive power of our language. Just as the ability to define procedures enables us to deal with processes at higher conceptual level than that of the primitive operations of the language, the ability to construct compound data objects enables us to deal with data at a higher conceptual level than that of the primitive data objects of the language. Consider the task of designing a system to perform arithmetic with rational numbers. We could imagine an operation add ret that takes two rational numbers and produces their sum. In terms of simple data, a rational number can be thought of as two integers, a numerator and a denominator. Thus, we could design a program in which each rational number would be represented by two integers, a numerator and a denominator, and where add ret would be implemented by two procedures, one producing the numerator of the sum and one producing the denominator. But this would be awkward, because we would then need to explicitly keep track of which numerators corresponded to which denominators. In a system intended to perform many operations on many rational numbers, such bookkeeping details would clutter the program substantially, to say nothing of what they would do to our minds. It would be much better if we could glue together a numerator and denominator to form a pair, so a compound data object that our programs could manipulate in a way that would be consistent with regarding a rational number as a single conceptual unit. The use of compound data also enables us to increase the modularity of our programs. We can manipulate rational numbers directly as objects in their own right, then we can separate the part of our program that deals with rational numbers per se from the details of how rational numbers may be represented as pair of integers. The general technique of isolating the parts of a program that deal with how data objects are represented from the parts of a program that deal with how data objects are used is a powerful design methodology called data abstraction. We will see how data abstraction makes programs much easier to design, maintain, and modify. The use of compound data leads to a real increase in the expressive power of our programming language. Consider the idea of forming a linear combination a times x plus b times y. We might like to write a procedure that would accept a, b, x, and y as arguments and return the value of ax plus by. This presents no difficulty if the arguments are to be numbers, because we can readily define the procedure linear combination. But suppose we are not concerned only with numbers. Suppose we would like to express in procedural terms the idea that one can form linear combinations whenever addition and multiplication are defined, for rational numbers, complex numbers, polynomials, or whatever. We could express these as a procedure of the form linear combination, okay? So we have two procedures where add and mul are not the primitive procedures plus and star, but rather more complex things that will perform the appropriate operations for whatever kinds of data we pass in as the arguments a, b, x, and y. The key point is that the only thing linear combination should need to know about a, b, and x and y is that the procedures add and mul will perform the appropriate manipulations. From the perspective of the procedure linear combination, it is irrelevant that what a, b, x, and y are, and even more irrelevant how they might happen to be represented in terms of more primitive data. This same example shows why it is important that our programming language provide the ability to manipulate compound objects directly. Without this, there is no way for a procedure such as linear combination to pass its arguments along to add and mul without having to know their detailed structure. Okay. We begin this chapter by implementing the rational number arithmetic system mentioned above. These will form the background for our discussion of compound data and data abstraction. As with compound procedures, the main issue to be addressed is that of abstraction as a technique for coping with complexity. And we will see how data abstraction enables us to erect suitable abstraction barriers between different parts of a program. We will see that the key to forming compound data is that the programming language should provide some kind of glue so that data objects can be combined to form more complex data objects. There are many possible kinds of glue. Indeed, we will discover how to form compound data using no special data operations at all, only procedures. These will further blur the distinction between procedure and data, which was already becoming tenuous toward the end of chapter 1. We will also explore some conventional techniques for representing sequences and trees. One key idea in dealing with compound data is the notion of closure. That the glue we use for combining data objects should allow us to combine not only primitive data objects but compound data objects as well. Another key idea is that compound data objects can serve as conventional interfaces for combining program modules in a mix and match ways. We illustrate some of these ideas by presenting a simple graphics language that exploits closure. We will then augment the representational power of our language by introducing symbolic expressions. Data whose elementary parts can be arbitrary symbols rather than only numbers. We explore various alternatives for representing sets of objects. We will find that just as a given numerical function can be computed by many different computational processes, there are many ways in which a given data structure can be represented in terms of simpler objects. And the choice of representation can have significant impact on the time and space requirements of processes that manipulate the data. We will investigate these ideas in the context of symbolic differentiation, the representation of sets, and the encoding of information. Next, we will take up the problem of working with data that may be represented differently by different parts of a program. This leads to the need to implement generic operations, which must handle many different types of data. Maintaining modularity in the presence of generic operations requires more powerful abstraction barriers that can be erected with simple data abstraction alone. In particular, we introduce data-directed programming as a technique that allows individual data representations to be designed in isolation and then combined additively. That is, without modification. To illustrate the power of this approach to system design, we close the chapter by applying what we have learned to the implementation of a package for performing symbolic arithmetic on polynomials, in which the coefficients of the polynomials can be integers, rational numbers, complex numbers, and even other polynomials. Okay, let's start thus with the paragraph 2.1, Introduction to Data Abstraction. Previously, we noted that a procedure used as an element in creating a more complex procedure could be regarded not only as a collection of particular operations, but also as a procedural abstraction. That is, the details of how the procedure was implemented could be suppressed, and the particular procedure itself could be replaced by another procedure with the same overall behavior. In other words, we could make an abstraction that would separate the way the procedure would be used from the details of how the procedure would be implemented in terms of more primitive procedures. The analogous notion for compound data is called data abstraction. Data abstraction is a methodology that enables us to isolate how a compound data object is used from the details of how it is constructed from more primitive data objects. The basic idea of data abstraction is to structure the programs that are to use compound data objects so that they operate on abstract data. That is, our programs should use data in such a way as to make no assumptions about the data that are not strictly necessary for performing the task at hand. At the same time, a concrete data representation is defined independent of the programs that use that data. The interface between these two parts of our system will be a set of procedures called selectors and constructors that implement the abstract data in terms of the concrete representation. Let me reread again this sentence. The interface between these two parts of our system will be a set of procedures called selectors and constructors that implement the abstract data in terms of the concrete representation. To illustrate this technique, we will consider how to design a set of procedures for manipulating rational numbers. Okay, here we have the first example, arithmetic operations for rational numbers. Suppose we want to do arithmetic with rational numbers. We want to be able to add, subtract, multiply, and divide them, and to test whether two rational numbers are equal. Let us begin by assuming that we already have a way to constructing a rational number from a numerator and a denominator. We also assume that given a rational number, we have a way of extracting or selecting its numerator and its denominator. Let us further assume that the constructor and selectors are available as procedures. So makeRet, taking two arguments n and d, returns the rational number whose numerator is the integer n and whose denominator is the integers d. Numer of x returns the numerator for the rational number x, and denom x returns the denominator for the rational number x. We are using here a powerful strategy of synthesis, wishful thinking. We haven't yet said how a rational number is represented, or how the procedures numer, denom, and makeRet should be implemented. Even so, if we did have these three procedures, we could then add, subtract, multiply, divide, and test equality by using the following relations. We can express these rules as procedures. Now we have the operations on rational numbers defined in terms of the selector and constructor procedures numer, denom, and makeRet. So here the selectors are numer and denom, and the constructor is makeRet, as the name suggests. But we haven't yet defined this. What we need is some way to glue together a numerator and a denominator to form a rational number. Pairs. To enable us to implement the concrete level of our data abstraction, our language provides a compound structure called a pair, which can be constructed with the primitive procedure cons. This procedure takes two arguments and returns a compound data object that contains the two arguments as parts. Given a pair, we can extract the parts using the primitive procedures char and cdr. Char and cdr, and thus we can use cons char and cdr as follows. So cons stands for construct. The names char and cdr derive from the original implementation of Lisp. That machine had an addressing scheme that allowed one to reference the address and decrement parts of a memory location. Char stands for contents of address part of register, and CDR, pronounced CUDR, stands for contents of decrement part of register. What the fuck? So constructors, we can define this here. This is let's see. Let's look at this definition. Define x. X is defined as a constructor of this pair. The pair is the first item of the pair is 1, the second item of the pair is 2, and we can access the first item of the pair, the first element of the pair, using char x, and we can access the second element of the pair using CDR. Okay. Notice that a pair is a data object that can be given a name and manipulated just like a primitive data object. Moreover, cons can be used to form pairs whose elements are pairs, and so on. Okay, so here Z is a pair of x and y that are two pairs, and so by applying recursively the procedure, the primitive procedure char and CUDR, we can access the elements of the elements inside the x or y. In the next section, we will see how this ability to combine pairs means that pairs can be used as general purpose building blocks to create all sorts of complex data structures. The single compound data primitive pair implemented by the procedure cons, char, and CUDR is the only glue we need. Data objects constructed from pairs are called least structured data. And this is the first time I see something like that. Because usually programming language books about programming and programming languages of course introduce pairs, but they don't introduce pairs as general purpose building blocks to create all sorts of complex data structures. They introduce pairs as special data structures that can be useful, and in some contexts that could be better than lists or arrays. But this is the first time I see pairs introduced as general purpose building blocks that could be used to create all sorts of complex data structures. So this is a real novelty, at least for me. But let's go ahead. Representing rational numbers. Pairs offer a natural way to complete the rational number system. Simply represent a rational number as a pair of two integers, a numerator and a denominator, and then make ret, numer, and denom are readily implemented as follows. So make ret creates a pair. Oh, yeah, another way to define selectors, of course. And in this case, we are just associating those names to the values of the primitive procedures. So in this case, when you call after these three definitions, when you call make ret, you are basically calling cons, and when you call numer or denom, you are essentially using char or CUDR to access elements inside the pair. In this case, we have a more verbose definition because we define make_ret as a procedure taking two arguments and applying the primitive procedure cons, and the same for numer and denom. Also, in order to display the results of our computations, we can print rational numbers by printing the numerator, a slash, and the denominator. Okay. And now we can try our rational number procedures. I'm sure there will be at least one exercise on this, so we will see uh, everything uh, in the next video, I think. As the final example shows, our rational number implementation does not reduce rational numbers to lowest terms. We can remedy this by changing make_ret. If we have a GCD greater common divisor procedure like the one in one of the previous sections that produces the greatest common divisor of two integers, we can use the GCD to reduce the numerator and denominator to lowest terms before constructing the pair. Okay, this modification was accomplished by changing the constructor make_ret without changing any of the procedures such as add_ret and malret that implement the actual operations. Exercise 2.1 define a better version of make_ret that handles both positive and negative arguments. Make_ret should normalize the sign so that if rational number is positive, both the numerator and denominator are positive, and if the rational number is negative, only the numerator is negative. Okay, this could be a nice exercise to do. I will do it later. Let's see. Let's see. Let's see what time is it. Okay. Abstraction barriers. Before continuing with more examples of compound data and data abstraction, let us consider some of the issues raised by the rational number example. We define the rational number operations in terms of a constructor make_ret and selectors numer and denom. In general, the underlying idea of data abstraction is to identify for each type of data object a basic set of operations in terms of which all manipulations of data objects of that type will be expressed, and then to use only those operations in manipulating the data. Data abstraction barriers in the rational number package. We can envision the structure of the rational number system as shown in figure 2.1. The horizontal lines represent abstraction barriers that isolate different levels of the system. At each level, the barrier separates the program above that use the data abstraction from the programs below that implement data abstraction. Programs that use rational numbers manipulate them solely in terms of the procedures supplied for public use by the rational number package. Add_rat, sub_rat, malrat, div_rat, and equal_rat. These, in turn, are implemented solely in terms of the constructor and selectors make_ret, numer and denom, which themselves are implemented in terms of pairs. The details of how pairs are implemented are irrelevant to the rest of the rational number package, so long as pairs can be manipulated by the use of cons, char, and coulter. In effect, procedures at each level are the interfaces that define the abstraction barriers and connect the different levels. Let's read it again. Procedures at each level are the interfaces that define the abstraction barriers and connect the different levels. This simple idea has many advantages. One advantage is that it makes programs much easier to maintain and to modify. Any complex data structure can be represented in a variety of ways with the primitive data structures provided by a programming language. Of course, the choice of representation influences the programs that operate on it. Thus, if the representation were to be changed at some later time, all such programs might have to be modified accordingly. This task could be time-consuming and expensive in the case of large programs unless the dependence on the representation were to be confined by design to a very few program modules. For example, an alternate way to address the problem of reducing rational numbers to lowest terms is to perform the reduction whenever we access the parts of a rational number rather than when we construct it. This leads to different constructor and selector procedures. The difference between this implementation and the previous one lies in when we compute the GCD. If in our typical use of rational numbers we access the numerators and denominators of the same rational numbers many times, it would be preferable to compute the GCD when the rational numbers are constructed. If not, we may be better off waiting until access time to compute the GCD. In any case, when we change from one representation to the other, the procedures add-rat, sub-rat, and so on do not have to be modified at all. Constraining the dependence on the representation to a few interface procedures helps us design programs as well as modify them, because it allows us to maintain the flexibility to consider alternate implementations. To continue with our simple example, suppose we are designing a rational number package and we can't decide initially whether to perform the GCD at construction time or at selection time. The data abstraction methodology gives us a way to defer that decision without losing the ability to make progress on the rest of the system. Okay, exercise 2.1. What is this? Okay, nice, I can do that. 2.3, implement a representation for rectangles in a plane. In terms of your constructors and selectors, create procedures that compute the perimeter and the area of a given rectangle. Now implement a different representation for rectangles. Can you design your system with suitable abstraction barriers so that the same perimeter and area procedures will work using either representation? Okay, I think I will do these exercises. Not sure if all of that, but at least a couple of, I will do at least a couple of exercises. So see you in the next video with what is meant by data. Bye bye. Or should I say, maybe I should say ciao ciao.